Today we will discuss the accumulation function, which is a continuation of what we did in our last video on the definite integral as area. We just are introducing it in a new form. So now that we know how to find the definite integral in terms of area, this is a very, very, very important type of problem, one that appears on the AP test all the time. And so we'll kind of explore it in an explorative type of way. Explorative, maybe. And then we'll get into the actual problems and how it appears on the AP test. So this is called the accumulation function. It says, suppose we're given a function f of x equals 2. It's a horizontal line because it's a constant function. Don't worry about like the variable. So notice that f of x equals 2 is the same thing as f of t equals 2, which is the same thing as f of k equals 2. So the independent variable doesn't change how the function is graphed or what it looks like. So there's a reason we're not using f of x in this case. There's a reason we're going to use f of t, and I'll explain it. It's because of this whole integral as an accumulator. And so notice that we have the integral from 0 to x, and it doesn't always necessarily have to start at 0. It could start at a different number, but whatever number it does start at, it will be a constant. But it goes to a variable x instead of to another number. When we were working with the definite integral as area in the last lesson, we were always given the two numbers, like the integral from 0 to 3, figure it out. The integral from 10 to whatever, figure it out. In this case, because we're integrating from 0 to x, this has now created a function. So it's no longer just a numeric value of like the answer being 7 or pi. Now it actually is creating a whole nother function for us because we can integrate to different values of x. Now, the reason we put this as f of t dt instead of f of x dx is because this variable inside of the integral and this variable as a limit of the integral are two different variables. So we can't call them both x because that would get confusing since we're talking about two different things. So we'll say that it's the integral from 0 to x, and then we'll just change this to be f of t dt so it doesn't confuse us. So let's complete this chart. The first one will be the integral from 0 to x, and here's all of our x values that we're going to plug in. So if the first x value we're going to plug in is 0, then this integral would be, and I'll write it in down here, the integral from 0 to 0 of f of t dt. Well, we already talked about how an integral from one number to the same number doesn't go anywhere, therefore the area under the curve is 0, so that would be 0. For 1, the integral from 0 to 1 of f of t dt is this rectangle right here, which has an area of 2 units. Now, I won't write that out every time because we're just adding rectangles. So the integral from 0 to 2, for this one right here, the integral from 0 to 2 would be from here to here. That's an area of 4 units. The integral from 0 to 3 would be from here to here. That's an area of 6 units. 0 to 4 would be 8 units, and 0 to 5 would be 10 units. So notice that as x changes, we have different outputs. So this is creating its own function, 0, 0, 1, 2, 2, 4, 3, 6, 4, 8, 5, 10. And we could actually plot those points on a graph, and if we plot those points on a graph, if we connected them, we would call that the accumulation function. So the integral from 0 to x is how it accumulates, and it creates its own function as you put in different values for x. So here is that function we were just talking about. So we're accumulating area, we're adding on more and more and more area. Notice that here we have a graph or another example, but a sketch of it. It says let's calculate the value from 0 to x of f of t dt for this new function for x equals 0 to 4, and we're going to complete this chart. So again, the integral from 0 to 0, right here, is 0. Let me write that in. Oops. There we go. The integral from 0 to 1, which is this triangular region right here, has a base of 1 and a height of 1, but it's a triangle, so it's 1/2 1 times 1, or 1/2. The integral from 0 to 2, 2 times the height of 2 would be 4, half of that is 2. The integral from 0 to 3, 3 times the height of 3 is 9, half of that is 9/2. The integral from 0 to 4, 4 times 4 is 16, half of that is 8. So again, notice these new values, 0, 0, 1, 1/2, 2, 2, 3, 9/2, 4, 8. We could plot those and they would create a function, and that would be the integral. or the antiderivative of this function. So let's look at it in this case. It says, let f of x equal the integral from 0 to x. So here we are at 0, and here's all of our different x values. It says, think of f of x as the rate of snowfall over a period of time. So for instance, at x equals 1, snow is falling at a rate of, if we look at 1, here's 1, 2, 3. So it's falling at a rate of 3 inches per hour. At x equals 3, so here's x equals 1, x equals 2, here's x equals 3. It says it's not snowing at all since it's 0. At x equals 4, snow is melting. When it's negative, it means it's melting at a rate of 4 inches per hour. So we're going to complete this chart based on these different values to kind of figure out what the snowfall looks like and how much snow has accumulated on the ground over time. So for the first one, since f of x is equal to this integral up here, the integral from 0 to x of f of t dt, the first value from 0 to 0 will be 0. Nothing has changed because we haven't gone anywhere from 0 to 0. The next one, the integral from 0 to 1. All right, let's start looking at some of these areas. The rectangle at the bottom has a base of 1, height of 1, so therefore the area is 1. The triangle has a base of 1, height of 2, but then divided by 2, the area is 1. So the integral from 0 to 1 is 2. Then, from 0 to 2, we add on this rectangle, which has a base of 1 and a height of 1, 2, 3. So we're adding on 3 units. So 2 plus 3 is 5. Then we get to 3. Here we have this triangle. This triangle has a base of 1, but a height of 3. Therefore, the area is 1.5. 1.5. So add that on to 5, and you get 6.5. Up to 4, it has a base of 1, height of 1, 2, 3, 4. So 4 times 1 is 4, and half of that, since it's a triangle, would be 2, and it's negative since it's below the curve. So we have 6.5 minus 2, because remember we're adding all these. So 1 plus 1 plus 3 plus 1.5 minus 2 gives me 4.5. At 5, this is the same triangle, so another negative 2. It brings me down to 2.5. Excuse me. This little teeny tiny triangle right here has a base of 1 and a height of 1. So the area is 1 times 1 divided by 2. That's 1/2, or 0.5. So now we're up to 3, because we're adding again. 6.5. Notice that they're asking at a half of an interval. So that's this little piece right in here. So this has a height of 1, but the base is actually only a half of a unit, because it's right in between 6 and 7. So if it's a height of 1 and a base that's a half, and then you have to divide that by 2, that would be 1 times 1/2, which is 1/2, times another half, which is 1/4, or 0.25. So it's 6.5, now we're up to 3.25. Now, by the time we get to 7, notice that it's the exact same shape as this one. So base is a half, height is 1. So 1 times 1/2 times 1/2 gives me a negative 0.25 since it's below the curve. So luckily by 7, that put me back to 3 again. So 3.25, then 3. And finally at 8, I have one more little rectangle down here at the bottom, and it has a base of 1 and a height of 1. Therefore, the area of that rectangle is negative 1. So 3 minus 1 puts me back down to 2 again. Hopefully you guys can see that. I know that it's kind of written over the top. So 3, 3.25, 3, and then 2. So we're going to answer some questions about these numbers. So we finished part A. Part B says, now let's consider f prime of x equaling the derivative of the integral function, so the accumulation function. So now we start getting into this idea of an integral, specifically the integral is an accumulator, and how it relates to its derivative, and essentially what that means. So in this case, we were taking the integral from 0 to x of f of t dt. We were taking the integral and adding together all of these values as we went from left to right, and that was giving us how much snow had accumulated on the ground at various moments in time. So for example, if you go back and look at your chart, After 3 hours, we had 6.5 inches of snow, or maybe feet of snow. Is it inches or feet? Inches, there we go. 6.5 inches of snow on the ground after 3 hours. Then if you look at your chart at 7 hours, there was only 3 inches of snow because some of it had melted, etc., etc. Now, sorry, too far. Here we go. For part B, it says, let's consider what happens if I take the derivative of that. So the function we were looking at was f of x, and now they're saying take the derivative of f of x. Well, the derivative of f of x on the left-hand side is the same thing as the derivative of what it's equal to. So if this integral is equal to f of x, then if we're going to take its derivative, we have to throw a d dx in front of it. So let's see what happens. It says, if we take the derivative of an integral, what would you expect to happen? And I hope that what you would expect to happen, since they're opposites or inverses of each other, is that they cancel each other out, essentially. So f prime of x equaling d dx of this integral from 0 to x of f of t dt. And again, with the notion that integrals and derivatives are inverse operations, meaning that they undo each other, we would say it's the same thing as f of t. So the derivative of an integral is the function inside of the integral. So notice that when I take the derivative of this integral, they are inverse operations, they undo each other, therefore I'm just left with f of t, the function inside of the integral. It says, knowing that, let's complete this chart. F prime of 0. Well, this is the graph of f of t, or f of x, however you want to call it. If this is the graph of f of x, to fill in this chart, I'm literally just going to read the values from the chart. So at 0, it says this function is equal to 1. At 1, it says the function is equal to 3. At 2, it says the function is equal to 3. At 3, the function is equal to 0. So I'm going to start filling in those numbers. At 0, it's equal to 1. At 1, it's equal to 3. At 2, it's equal to 3. At 3, it was equal to 0. At 4, right here, at x equals 4, it's equal to negative 4. At 5, it's equal to 0. At 6, it's equal to 1. At 6.5, it's equal to 0. At 7, it's equal to negative 1. And at 8, it's equal to negative 1. So the derivative of an integral is the function you started with at the very beginning. Part C says, on what subintervals of 0 to 8 is f increasing? Now, before we get into answering this question, I briefly want to talk about, one more time, like what's going on here and how we know what's going on and the relationship between what's going on. So, this brings us back to function analysis, and this is kind of where we come second semester full circle back to function analysis again, and being able to look at a graph and look at its derivative and look at its second derivative to figure out information about the other pieces. One of the things that we need to be aware of is that the relationship between these functions. So, let me make a little chart over here. F of t, or f of x in this case, is actually the first derivative. You guys might want to write this down in your notes. It's actually the first derivative. If we look at the units on it, it's inches per hour. Hopefully that kind of gives away that it's the rate at which something is changing. When we take its integral, we got this function f of x. This was the original function. So we're looking at a graph of the first derivative, f of x. If you take the integral as an accumulator, the integral from 0 to x, it gets us back to capital F of x, which was the original function. The units on that were just inches. It told us how much snow had accumulated on the ground over a period of time. We could technically take the second derivative, and that would tell us how quickly the rate is changing. But right now we won't look at that because there's not much application to what we're talking about right now in terms of that. So what I really need you to understand is that the graph we're looking at is a graph of the first derivative, f of x is the first derivative, and that when you take the integral as an accumulator, when you have this integral in front of it, the integral from 0 to x, when you go through that whole process of integrating and using it as an accumulator, it gets you back to the original function. And then again, taking the derivative of that integral puts us back to the first derivative again, just like we looked at in part B. So, part C says, on what subintervals from 0 to 8 is f, capital F, increasing? So if I want to know where a function is increasing, I will look for where its first derivative is positive. So this first derivative is positive from 0 to 3, and then again from, 5 to 6.5. And if I want to know where a function is decreasing, I'll look for where its first derivative is negative. So the first derivative is negative from 3 to 5, and then again from 6.5 to 8. Now, if you look back up at part A, you'll notice from the table that hopefully this makes sense to you. In part A, notice how from 0 to 3 the numbers were going up. So it was at 0, and then there were 2 inches of snow on the ground, and then 5, and then 6.5. Then from 3 to 5 it was decreasing. It started going down. From 6.5 it went down to 4.5, and then down to 2.5. Between 5 and 6.5 it went back up again. It was increasing again. It went from 2.5 to 3, then 3 to 3.25. And then it was decreasing again for the rest of the time. From 3.25 it went down to 3, and then down to 2. So notice how the level or the height of snow on the ground from part A is directly related to the function increasing versus decreasing that we're talking about here in part C. D says, where in the interval from 0 to 8 does f achieve its minimum and maximum value, and what are those? So the very smallest value that it reaches is 0. At the very beginning, there's no snow on the ground. So the minimum would be at time equals 0, and f of 0 is equal to 0. There was no snow on the ground at 0 seconds. The maximum would be at time equals, and the highest amount of snow, or the most amount of snow that on the ground at any moment in time, was at t equals 3 seconds. And f of 3 was equal to 6.5. That was the most amount of snow on the ground. Now, looking at the graph, let's talk about how we would have known that from the graph. First of all, at 3 we have a maximum. We also have a maximum over here, however, it's 6.5. But if you look at your chart in part A, you'll notice that at 3, the height of the snow was 6.5, but at 6.5, the height of the snow was only at 3.25. So obviously this one is the maximum, or the absolute maximum. You can kind of tell, by the way, because if you're starting here at 0 and there's no snow on the ground, you're accumulating this big positive area, and then you do lose a lot of it. Like, look how much of it you lose. But then, when you come back over here, this little tiny triangle doesn't make up for as much as you lost. So if we're at a maximum right here, we're accumulating. We get to this maximum, then we start to lose some, but we never actually regain as much as we had lost. And you can just kind of tell that by looking at the areas and how big they are. So again, maximum occurs here at 3. The minimum, this is a minimum right here, but remember we also have to check the endpoints. So if you look at this first area, if it started at 0, we have this first big area, and these two, or this triangle here, I should say, doesn't cancel out completely the area that we had from the beginning. And so that's how we know that this would have been the maximum because of that. And then last but not least, part F says, find the concavity of F and any inflection points and justify your answer. So remember, for inflection points, points of inflection are the maxima and minima on the derivative graph. So that would be this one right here. The points of inflection are at x equals, let's see, it has, so right here, what's happening is that it's increasing, the derivative is increasing, which means that the original function is concave up. But then it goes flat, which means that the original function is still increasing, but at a constant rate. And then it goes down, so now it's concave down, so it's increasing at a decreasing rate. Now, technically that's not one point of inflection, it's just kind of like a range of inflections. So keep that in mind, but it still does change its concavity in the sense that it goes from a concave up function to a function without concavity at all, from 1 to 2. However, this is definitely a point of inflection at x equals 4. And this is definitely a point of inflection at x equals 6. And then in terms of the other intervals, we'll just say concave up from 0 to 1, union, what was that, 4 to 6. We'll say it's concave down from, sorry, that's my dog again. Concave down from 2 to 2 to 4. 2 to 4, and then again from 6 to 7. And last but not least, there's no concavity. There's no concavity wherever the function is constant. So from 1 to 2, and then again from 7 to 8, there's no concavity. All right, so we get to sketch a rough graph of what f of x looks like. And I want you guys to use the points from part A. So I want you to actually plot them here now. So in part A, we said that our points were at 0, 0. 1, 2, 2, 5, 1, 2, 3, 4, 5, 3, 6.5, 4, 4.5, 1, 2, 3, 4.5, 5, 2.5, 6, 3, 7, 6.5, 3.25, 7, 3, and 8, 2. And then when we connect these, it's pretty obvious where the intervals of increasing versus decreasing are, and the maxima and minima. But I want you guys to be careful for the points of inflection and the concavity. So it says that we have a function that's concave up from 0 to 1. So try to make it pretty drastic that it's concave up. Then it says it has no concavity from 1 to 2. So I want you to just draw a straight line that connects those, neither concave up nor concave down. From 2 to 4, it's concave down, so connect those with a frown. From 4 to 6, it's concave up, so connect those like a cup. From 6 to 7, concave down. And then last but not least, again, there's no concavity from 7 to 8, so connect those with a straight line. So this is what the snowfall looks like over time. And again, you can see that it's falling. It reaches a maximum after 3 seconds. And you can see where it has maxima and minima. It just, its absolute maximum, is at 3, and its absolute minimum is at 0. All right, I believe that's all for today. So we're going to stop there. We'll pick up the rest tomorrow.